In this lesson, we are going to talk about trig substitutions. Now, in the last lesson, we talked about trig integrals, and this time we are talking about the substitutions which involve a trigonometric function. Now, when do we actually use these substitutions? Well, these trig substitutions are used usually when you have an integral in which there is a radical appearing. But once again, not all radical integrals need trig substitutions, some of which can be attacked using a normal U substitutions. But there are radical integrals for which you will need trig substitutions. Now I have shown you three types of integrals. Now if you look at the first example, you will see one type. You can see you see a radical here? Yeah, the radical is of the type a number minus x squared type of radical. Now in the second one also there is a radical, and this one is something x squared plus a number. So in the previous one a number minus x squared, here is x squared plus a number. And the third radical is an x squared minus a number, which is different from a number minus x squared. And why is that? Because someone might think that, oh, can't I take a negative sign outside and make it look like this? Well, if you take a negative sign, if you take it outside the radical, you will see that you will actually get a radical of -1, which is an imaginary number. So really you can take a negative out of this and then make it look like this. So remember that when you have a number minus x squared and x squared minus number, they are two different things, and you need two different trig substitutions. Well, as before, let's start with an example for which we will not need a trig substitution, a radical which can be nailed using a normal U substitution. Well, if you take this one, now here you don't really need a heavy duty trig sub. You can start with the U substitution. Why? Because if you call this thing U, then the derivative of U will be 2x, and that 2x is right up there in the leftover part. Okay, which means so the derivative of substitution cancels off the leftover part. So it's a good example for a U substitution. Okay, but you will see later that if you take an example like this, well, then you cannot use a U substitution. Why? Because if you call this U, for example, then the derivative of U would be -2x, but there is nothing up here to cancel that -2x. So the U substitution will not work here. Then what will work here? Well, you can say that it is an integral of the type where you have a number minus an x squared. So we like to call that type a squared minus x squared, where a squared is the square of a number. Okay, so whenever you have a radical where you have a number minus x squared, the best bet is to use a trig substitution of the type x equals a sine theta. Okay, now what is a? A is actually the square root of the junk here. So in this case, a squared will be 9. Okay, that's the very first thing that you should do, is to try to figure out what a is. So a squared is like 9, which means a is 3. So the substitution will be x equals 3 sine theta. Okay, so we'll try the substitution x equals 3 sine theta, which will mean dx is equal to 3 cosine theta. Now we plug everything back in, so the dx will become 3 cosine theta d theta. Okay, and inside the radical we have the 9 as it is, and instead of x we plug in 3 sine theta square. And now when we expand this, we will still have 3 cosine theta over here, and here you have 9 minus 9, we have sine squared theta. Now you will notice that in all these examples, right, that we will do, you can take the 9 outside the radical. Now when you take the 9 outside the radical, that becomes 3. And inside the radical, now the 9 is gone, so you will have 1 here, 1 minus, and then you have 1 here, so 1 minus sine squared theta. Now at this point, if you pause a little bit, you will know something wonderful happens, because now what is inside the radical is 1 minus sine squared theta. Now by Pythagorean, we know that 1 minus sine squared theta is cosine squared theta. So the cosine square theta, so this actually becomes cosine square theta. Now why is that useful? Because now we have the square root of cosine square theta, which is thus cosine theta. So now you will know the usefulness of this substitution. Because of this substitution, we managed to get about minus sine square theta radical, which turned out to be cosine theta, and the radical just disappeared. So this substitution really helped us to remove the radical. So the radical is here, but when it comes here, the radical is no longer there. And now it becomes even easier because the 3 cosine theta cancels with 3 cosine theta, and you just have 1. So you need to integrate 1 with respect to, remember, with respect to theta, not x. But integral of 1 would be then just theta. Okay, but you need to put a constant here though. But you can't leave the answer as theta, you need to plug it back. Now, how you need to convert this into x, because we started the integral with x. See? So we need to give the answer also in terms of x. So how do we do that? Now we know that x is equal to 3 sine theta. We need to solve this for theta. So first we solve it for sine theta. So we solve it for sine theta. Then sine theta would be equal to x divided by 3. If sine theta is equal to x divided by 3, we can solve for theta, which will be theta is equal to what? Inverse sine of what? X over 3. So the answer would be theta, so we plug it back here. So theta is sine inverse x over 3. So sine inverse x over 3 plus a constant. That's your answer. Now this is a kind of a straightforward example. Now let's look at a more challenging example. Now let's look at this example. Okay. Now again, this has a radical. Now is the radical of the type number minus x squared? Yeah, the number is 4, right? Okay. So then definitely we know that the substitution would be of the type x equals a sine theta, because it's number minus x squared. Now the first job is to find a, and how do you do that? A squared is like 4. So what you do is you take a squared and equal it to the number which is here. So the number which is here is 4. So a squared is equal to 4, which means a is equal to 2. Really a is equal to plus or minus 2, but we only take a equals 2 because we just need one substitution. So if plug in a equals 2 here, then we can get x is equal to 2 sine theta. So we have x equals 2 sine theta. And we take the derivative, we get 2 dx is equal to 2 cosine theta d theta. Now we go up here and we plug everything back. So so we have what? So this becomes 2 sine theta cube. So 2 sine theta cube. This becomes 4 minus 2 sine theta square. Or I need to plug in for dx also here. This might make sense. So dx would be 2 cosine theta d theta. Okay, so now once again let's concentrate. So 2 cube is 8, so 8 sine cube theta and 2 cosine theta. Let's concentrate on the inside part. 4 minus and then 2 squared will be 4, and then 4 sine squared theta. So now we take the 4 outside, then it becomes 2, and then we have 2 outside, so 8 and 8. Then the inside, the 4 is no longer there, so this becomes 1, this becomes 1 minus sine squared theta. So as before, we have 1 minus sine squared theta appearing in the radical, which is good news because we know that that is equal to cosine squared theta, and the cosine squared theta radical is nothing but cosine theta. So this part becomes cosine theta. So we have 8 sine cube theta, 2 cosine theta, 2 cosine theta. So now if you get these terms together, we have cosine theta, it means cosine square theta, and sine cube theta, and we can take 2 times 16, 16 times 2 is 32, and 32 can be taken outside, but that's not the end, right? It's not the end, we need to continue this, right? Why? But now it is an integral that we can handle, right? Why? Because this is a trig integral with sine and cosine with sine odd power, and you know how to do that, right? So you can separate this, split this into 2 parts, and then take the side out that side and convert the, like we did it before. Okay, so basically we just looked at one type of radical so far, when we have a number minus x number minus x squared, but we will be doing the other two types, that means number plus x squared as well as x squared minus a number in the next lessons. But for the time being, I'm going to leave you with a video exercise, and that will be to evaluate 1 over square root 16 minus x squared, which is exactly like the ones that we did before. Thank you.